Hello Year 11. This video that I'm doing today goes with exercise 14G of your text. The exercise is called Graphs of Sine and Cosine. But as usual, because this whole chapter is about circular functions, we actually start with the unit circle. Because in order to draw the graphs of sine and cosine, you need to actually have an appreciation of the patterns created by the unit circle. So the reason I've got this in front of me here, in front of us, is that this unit circle has these four coordinates shown. Okay, 1, 2, 3, 4. Okay, and the x coordinate of each of those pairs is the cosine value for the particular angle at that point, and the y component is the sine value for that particular angle at that point. So on this one here at 0 and also at 2 pi, cos 0 is 1, sine 0 is 0. Okay, so actually let's just go with the sine values. The sine values are the y values of these pairs. So the sine of 0 is 0. The sine of pi on 2 is 1. The sine of pi is 0. The sine of 3 pi on 2 is -1, and again the sine of 2 pi is 0. Okay, now what we can do with these values is that we can actually plot these values on a set of axes. Okay, and when we plot these values on a set of axes, we get something like this. In fact, we get this. Okay, so this top graph, this is a graph of y equals sine of x. Okay, sine of any angle. And look, by the way, when you see these graphs, they can be drawn in terms of they can be drawn with the axes y and x, and sometimes you also see them with the axes y and t for time, because a lot of applications of these trig functions refer to time periods. Okay, so what we've got here is we've got the sine of 0 is 0. Okay, the sine of pi on 2 is 1. The sine of pi is 0. The sine of 3 pi on 2 is -1. And the sine of 2 pi is 0. Okay, so we're going from 0, -1, 0, 0, 1, 0, -1, 0. And what the function is actually doing, because you're going around in a circle, is it's oscillating between -1 and 1, passing through 0. Now this axis length here, the axis length from 0 to 2 pi, that represents one revolution of the circle, one turn of the circle. Okay, and so therefore it also represents one period on the sine graph. For those of you that can remember from your science, whenever we do wave physics, we talk about the period of a wave, and we also talk about the amplitude of a wave. This period is also known as the wavelength. Okay, so wavelength is equivalent to period, and if you're using a unit circle with no transformations or changes to the graph, the wavelength or the period of the graph is 2 pi, one revolution of the circle. Okay, so the top one is the sine graph, bottom one here is the cosine graph. Okay, so and you get the cosine graph, as you can imagine, you get the cosine graph by looking at the other coordinate, by looking at the x coordinate. Okay, remembering that from there to there is the cosine value of angle 0. So cos 0 equals 1. Cos 90 equals 0, or pi on 2. Cos pi equals -1. Cos 3 pi on 2 equals 0. Cos 2 pi equals 1. So it oscillates. It's starting at 1. Okay. So as you can imagine, it's the same shape of a graph. Okay, but everything has been shifted. Or you could almost imagine the bottom graph is the top graph, but it's just been shifted either that way or that. Actually, it's been shifted back this way. Okay, because cos 0 is 1, cos pi on 2 is 0, cos pi is -1, cos 3 pi on 2 is 0, cos 2 pi is 1. Okay, so the graph has the same shape, it has the same amplitude, it has the same period, but it's been shifted. Okay, and sometimes that's referred to as a phase shift. Okay, but this is y equals sine x, this is y equals cos x. All right. What I'd recommend you do, just to take a second to do it, is to actually get your CAS out and just get your CAS to graph them. Okay, just graph y equals sine x and graph y equals cos x, and just sort of play with it a little bit. Okay, where do we go next with this? Alright, so that's the sort of information that you can find. This is all on pages 496 and 497 of your text. All of this, okay? Where it goes to next, though, is it goes to variations of the function. Okay, so this is just the same graphs, but what I've actually done is I've whited out these values, and you'll hopefully appreciate why in a minute. So actually, I'll go to this page first. Okay, so because it's not as easy as just saying, well, y equals sine x, y equals cos x. Okay, because trig functions are not just these standard base trig graphs. Similarly, when we talk about quadratics and we talk about y equals x squared, we don't just deal with y equals x squared. We deal with functions in the form of y equals ax squared plus bx plus c. Okay, so when you deal with quadratics, and they're called y equals ax squared plus bx plus c. Similarly, when you deal with trig functions, you've got y equals a sine nt and y equals a cos nt. Okay, so these are variations on the basic sine and cos graph. So these are like the general equations. Okay, so like with your regular sine graphs, y equals sine x or y equals sine t and y equals cos t, the period is 2 pi. Okay, but if you have a graph with a coefficient in front of the t or the x there, the period is actually 2 pi on n. Okay, the period is changed to 2 pi on n. Okay, also this coefficient in front changes the amplitude of the graph. Okay, so because if you said, well, okay, so I'll stop saying okay, Mr. Leeson, y equals sine x. Okay, if y equals sine x, you can have a value of 1, but if you've got this coefficient in front, then you multiply that value of 1, the radius of the unit circle, by that value. So the new amplitude of the graph becomes a. The maximal domain is R. It says that in your book because these graphs can go on forever in the positive and the negative direction unless you actually restrict the domain. And some of the questions we do actually restrict the domain. Okay, and the range of these trig functions is negative a, positive a. It's got to do with whatever the amplitude is. So if it's just the unit circle, it's -1 to +1. But if there's a coefficient here, then the range is actually multiplied. 1 is multiplied by this coefficient. So there you have it. All right. Now, the first thing you're asked to do in this exercise, there's some examples and some information on page 498 about what happens when you have these values. Okay, so what I might actually do here is it says for each of the following state the amplitude and the period. Okay, so when you have the function f of t, bearing in mind we can use t or we can use x. Let's move that way a little bit. Whoops. Okay, we've got f of t equals 2 sine 3t. So the amplitude of the function is 2. It's just that coefficient. And the period is 2 pi divided by whatever this coefficient here is, 2 pi over 3. So that's the period. Okay, and I've got a couple of others here. If the function of t equals half sine t on 2, a equals -1/2, n equals 1/2. Okay, so the amplitude still equals 1/2 because it's plus or minus. Alright, the period is 2 pi divided by 1/2. 2 pi divided by 1/2 is actually 4 pi. when we have in the next one here, this is a cos graph, okay, but it's the same idea. The amplitude is 4. This n value, this coefficient is 3 pi. So the amplitude becomes 4, as was said, and the period is 2 pi divided by 3 pi, which is 2/3. Okay, there's no pi values on the x-axis here, which is relatively common when you're dealing with trig functions. So what I thought I would do is actually show you how graphs like this are sketched. Okay, so if we have this here, I'll use my pencil. We want to graph f of t equals 2 sine 3t. So this is our sine graph. F of t equals 2 sine 3t. So if I want to graph that, then the amplitude is 2. So over here, that value is 2, that value is -2. Right, so it's going between 2 and -2. Okay, and the period is 2 pi on 3. Okay, so instead of being 2 pi, this value becomes 2 pi on 3. Okay, so what it actually means is that between 0 and 2 pi, I can't really show it here, between 0 and 2 pi, you can fit in 3 wavelengths. Because this is 2 pi on 3. So in one revolution of the circle, if you like, it's 2 pi on 3. So the wavelength is... The normal wavelength, sorry, is 2 pi. The normal period is 2 pi. I keep saying wavelength because I'm a physics teacher. Okay. The normal period is 2 pi. This period is 2 pi on 3. So you can fit 3 in 0 to 2 pi. Okay. Having a coefficient, having a whole number here, or an integer there, or a value greater than 1, has the effect of compressing the graph, of shortening the wavelength. Okay. If you have a fraction in here, it has the effect of lengthening the wavelength. Okay, so looking at my third example that I had on this page, f of t equals 4 cos 3 pi on t, if I was to actually apply that to here, this value here would be 4, this value here would be -4. The period, focus, the period is 2 pi divided by 3 pi, so the period is 2/3. So this value here, actually, sorry, this value here is 2/3. Okay, 2/3. So this value here is 1/3. So this value here is 1/6, and this value here is 3/6. So this is, yeah, this is a half. All right. So these are not values of pi for t in this case. These are just fractions of whole numbers. Okay. But one period is the length 2/3. What's interesting here is in this example, f of t equals a half sine t on 2. The amplitude is, there's a negative here. Okay, the amplitude is a half, n is a half, so the period it becomes 4 pi. So it's a sine graph, so this would be 4 pi. But this negative here has the effect of flipping the graph that way. Okay, so if I was to draw this graph, f of t equals a half sine t on 2 on this set of axes, that negative here means what I'd need to be doing is drawing like the reverse of this. So it would be doing this, it would be doing this, it would be... let's see if I can get this right. It goes up to about there, so there like this. Those are tricky to draw freehand. Okay, that's the first period. Right, so drawing f of t equals negative a half sine t on 2. The period is 4 pi, so that would be 4 pi, and this would be negative a half. Okay, that's a little bit messy, but what I suggest you do with a function like this, okay, is get your cas out and graph y equals sine x, and then on the same set of axes graph this function y equals negative a half sine t over x over 2, and just see the difference, see what it's doing. Okay, a good way to actually learn these and get an appreciation is in not just watching the videos that I make, but using something like your cas to actually play with it a little bit and practice drawing these graphs. One of the outcomes for methods is being able to actually use the technology. And yes, we do some assessments that are tech-free, but that doesn't mean you can't actually use your CAS to help you learn. Okay, that's the basics of it. All right, that's the basics of the shape of these graphs. There are worked examples 12, 13, 14, 15, and 16 to look at where they go through some of this. Okay. Example 16 is the one I was just talking about, where when you have a negative value here, this negative value actually reflects the graph, if you like, in the x-axis. So have a look at that. All right. Take a look at them. Practice drawing a few. Come back to your teacher if you've got some questions. But as I said, that's the basics of drawing graphs of sine and cosine. I hope this has been helpful. Thanks, guys. I'll see you next time.